section in chapter 4 is about application and models of exponential growth and decay. And so as we look at growth and decay, we're looking at this equation, y equals y sub 0. And sub 0 just represents, the initial amount, or the amount at the present time. Amount of material, or grams, whatever you're dealing with. And K is kind of like your rate, is your constant. Kind of like your rate. So this looks very similar to A PERT, right? Your principal times E raised to the RT, right? So it's very similar to A PERT, if not really the same. I mean, just this equation deals with exponential growth and decay. So that's the formula that we're going to use. And time is usually in years, unless otherwise directed. All right, it's in years. And you notice that when t equals 0, so if t equaled 0, that'd be at time 0, right? So or at year 0 or whatever. So if I plug that in, that'd be 0 raised, or 0 times k. And what is 0 times k? That'd be 0, right? And what's e to the 0? Isn't that 1? So this would be just y sub 0. So y equals y sub 0 when t equals 0, right? So that's why it's the initial amount, right? This is the initial time, 0, and I get my initial amount. And when k is bigger than 0, when that constant rate is above 0, that means we have a growth, exponential growth. And when k is below 0, we have a decay, exponential decay. And so we'll kind of look at some examples of these, dealing with exponential growth and decay. And that's pretty much a lot of it, is just using this A PERT equation, or this exponential growth or decay function, and then just either finding out what your K is, finding out what your T is, or finding out just what your initial amount is. And whenever you're finding an initial amount, whenever you want to find y sub 0, plug t equals 0 in, right? And solve, and it's going to be your initial amount, right? So that's kind of how you do it. So let's go ahead and do some examples. So here's first one's dealing with carbon dioxide. In the year, this is 1990. And so we want to find out, okay, we want to find the exponential function, so we want to find this function. So we want to find this function. Well, we can go ahead and let, our initial amount, right, our t, or you can say t is x, you can say xy, or ty. Oops, switch that around. X, y, or ty. So you can let x equals 0 or t equals 0 means 1990. Okay, so that means if x equals 1, that'd be 1991. If x equals 10, that'd be the year 2000. Okay, so let's go ahead and plug in at year 0, what is my initial amount, right? I could plug in that I could plug these numbers in. What's my y at 1990? That's 353, right? Y sub 0 e k to the 0, right? But I don't need to do that because I know when my t is 0, isn't y sub 0 equal to y? And my y is 350, so y sub 0 equals 353. Okay, so now we can start writing our function. Y equals 353 e raised to the k t. Now we have to find our k. Okay, so to find the initial function, when I ask you to find the model or the function that represents something, you're finding all parts except for your two variables, and our two variables are t and y. All right, our time and our years, because then we can find anything in between 2,275 and 1990. Okay, so now we need to find that k. Well, we can use any of these that we want to, except for the first one, 1990, the initial amount. So we can go ahead and plug in any one of these that we have. So let's go ahead and do the last one. So the year 2,275. What does that represent for x or for t? Well, how many years is that past 1990? Isn't that 285? Right? 1990 minus 2275. That's 280. So t equals 280. And what is my y value? Isn't that 2,000? Okay, so let's go ahead and plug it into this formula that we got so far. 2,000, so our y equals 353. E, k, and our t here is 280. So now I'm trying to find the exponential right here, right? I'm trying to find that k, that exponent k, and like variables in my exponent, right? So I got to solve this exponential equation. Well, how do we do that? First, we got to get the base by itself. We practice these last section. All right, so we go ahead and divide that on our calculator. And as long as we don't get a decimal that goes on forever, then we can go ahead and take whatever this number says. But if it goes on forever, which normally it should, go ahead and just leave that as a fraction. You can reduce it the best you can, but go ahead and leave that as a fraction, because that will keep our value more exact, right? If I round it, that means I'm not being exact anymore. Okay, and it's okay. So leave it as a fraction. Now, how do we get that variable that's in an exponent by itself? Now we take the ln of both sides, and this needs to be in parentheses. And then we can use our properties of exponents, right? It says I can take this here exponent and move it out in front, right? Come on now. So ln of 2,000 over 353 equals k times 280, right? Times ln of e. And what does ln of e equal? It equals 1. And then so on my calculator, what I want to do after I divide by 280 here, on my calculator, I hit ln, comes up with the parentheses, hit 2,000, hit divided by, hit 353. You can end your parenthesis. You could hit enter here and then just say divide, and then after that hit divided by 280, or you can go ahead and close that parenthesis and then hit divided by and do 280. If you don't put this parenthesis in here to close it off, it will take 353. It will probably take 2,000 divided by 353 and then take that answer and divide it by 280 and then take the ln of that. Okay, so that's why this parenthesis right here matters. Okay, so when you do something like that, you get close to your k would equal, right, because this is equal to k. Your k would be approximately, let's see here, approximately, let's type it in, see what we get for our k. And we get 0.00609, and it goes on forever, right? So I did round it eventually, which probably would have been fine if you rounded the 2,000 over 53 to begin with. But this number right here is more exact of your k than this number, because I round it, right? That's approximate. Okay, so now we can just go ahead and put that rounded one in there. It's fine. So now we have our equation. We have our y sub 0. We now have our k. And it is a positive k, right? Since it's a positive k, and we can kind of tell that because our numbers are growing, right? Our numbers are growing, so it's a growth. So it's an exponential growth. So there's our function. Now we can go ahead and solve for, we could solve for any other year that we want, but we just want to make sure that when we do this, we are in between those years, right? So we don't want to really put in numbers when we put on our next t over 2,275, right? These numbers, because of our k was used by one of these numbers, we're going to be more accurate if we pick dates in between here. So we kind of want to pick dates in between there. So I think the next part of the question asks for year. When will it double? Estimate when the carbon dioxide will double. Double from 280. So when will it double from 280? And so we can go ahead and find that. So if we double 280, that'd be 560. So that would be our y that we're after. So we're trying to find out in what year will the amount 280 be doubled. And so now we're solving for t, right? We divide by 353. Same kind of thing as when I put in the year, or not the year, or the year, what, 285? 280, did I say 280? 285. 280, it should be 285. Alright, this should be 285. 285, 285, 285, 285. But you still get that K, because I took that K from the book. Alright, back on track now. Alright, so 560 over 353. Then that's going to be divided by our K, right? Just like this one up here was divided by our T, right? Didn't have what amount we wanted. Divided by the initial amount, the ln of that, then divided by our year. But here we're not finding our K, we're finding our year. So this time we take that, the y that we have, divided by our y sub 0, take the ln of that, and then divide that by our K, and that will give us our T. Okay, so we type that in, and our T is probably approximately 75.8 years from 1990, right? So that's from 1990. So that's about year 2065. Right, so in the year about 2065, you know, according to this model. All right, so there's one example of exponential growth. We can look at exponential growth in another way with finances and basically a PERT, but remember what I said from before, a PERT is really the same thing. So here we go, we got 3% interest compounded continuously to double. So here's our a PERT, right? Same exact equation, right? Y equals y sub 0 e raised to the kt. Same equation. These are the same. So we want to know when will it double. Double means if we invest P, then double would be 2P, right? So A would equal 2P, so 2P equals PERT. Double, right? So then we can go ahead and solve for our base E, so we can divide by P on both sides. Then we can get our exponents by themselves, right? And our rate is 3%, so we can go ahead and actually enter that in as well, right? So our rate 3%, we need to change it to decimal form, so that's 0.03. So that's 0.03 here. Okay, and then we can take the L. This, remember, P over P is 1, so we just get 2 equals E 0.03T. Now we can go ahead and take the ln of both sides. That the exponent's going to come drop down in front. And ln of E is equal to 1. ln of E equals 1. Divide by 0.03. And there we have our equation, right? So it's going to take, at 3% at a continual interest, it's going to take about 23.1 years, so approximately 23 years to double. Right. Okay, so when we look at half-life, we're looking at how long will it take a radioactive substance to become half that amount, right? Half-life. So how long is it going to take a radioactive substance to be half the amount of its initial amount? Okay, so suppose we have 600 grams of radioactivity substance, and we have our initial amount. That's our initial amount, and we have, in 3 years, we have 300 grams remaining. Okay, so in 3 years we have 300 grams remaining. We want to determine the exponential equation that models this, so we want to write our equation that models this. So we can go ahead and start with our, now notice that we get less, right? We get less amounts. That probably means that our K should be negative, right? So we start with 600, right, and we get out 300. So basically what we're trying to solve for is our K here. So we know we're going to get half, right? So when I divide by 600, when I get that E by itself, shouldn't I get a half? Right? And now we can go ahead, and our time is 3 years, so we can also enter that in, right? So our time is 3 years. Now we can go ahead and take the ln of both sides. Remember that exponent's going to come out in front. ln of E equals 1, so we just get K3 equals ln of 1/2. Divide by 3, divide by 3. So our K is approximately, it's going to be a negative, right? Because we've taken ln of 1/2, and ln of 1/2 divided by 3 is approximately negative 0.231. So there's our K. So then our equation is y equals our y sub 0, which is our initial amount, which is 600, e raised to our K, which is negative 0.231, and then times by our t. So there's our equation. Okay. Now we want to find out, okay, how much will be left after 6 years. So when t equals 6, what happens? Or how much do we have? So let's go ahead and use our equation that we just came up with. And our t is 6 this time. So we can actually just enter that just like that in our calculator, and we'll get y equals, put that in your calculator, and we get about 150. So 150 grams. Okay. So that's kind of how you do problems like that. We can also look at carbon dating and stuff like that to figure out what is the half-life equation for carbon 14, which is given here. So carbon 14, carbon dating, here's your equation, right? So your initial amount, so we can find out the time for carbon 14. How long does it take a half-life? So what's a half-life for carbon 14? Okay, so we're solving for T. So a half-life, you could start this is like the doubling one for a pert, right? So you could start with any y sub 0, but you're going to get half out, right? So whatever you start with, half, I start out with y sub 0, what's half of that? Half of that would be 1/2 of y sub 0, right? That would be a half. So you can go ahead and write it like that. Or if you want to put in numbers, you can put in numbers. You know, go ahead and put in 5. So what would you get out? That'd be 2.5, right? And people that are just looking at the notes here, they're going to be confused of where did 5 come from, or where did that come from, right? But when I divide by 5 on both sides, aren't I going to get a half? So I'll do this for people to know. So when I divide by my whatever this is, say it's 5, and I take 2.5 and divide it by 5, aren't I going to get a half? That's the whole point of a half-life. Okay, now how do we get these by itself? Of course, we take the ln of both sides, right? And what do I do with that exponent here? And then what does ln of e equal? Alright, so I'm just going to get negative 0.001216t equals ln of 1/2. And then I can divide by 0.00 negative 0.012001216 on both sides. And so then the half-life of carbon-14 is 5,700 years, right? Okay, and then we can answer any questions like that. Okay, if we have charcoal from an ancient fire pit and it contains 1/4 of carbon-14, and with a sample the same size, what's the age of charcoal? So I have 1/4 left, right? So that'd be 1/4 of whatever I start with. 1216t. And then so divide, I get 1/4 equals e minus 0.001216t. I can go ahead and solve for my t. I got to take ln of both sides, right? So basically I'm going to take ln, 1/4, not 1/2. We already know the answer to 1/2. Divided by 0.001216 equals our t. And so t is equal to 11,400 years. Okay, so here are some problems I can do: 15, 17, 19, 21, 27, because they're really almost all the same. On page 457, right? They're all using the same exact equation. Either it's y sub 0 ekt or p-e-r-t, right? They're the same exact equation. If your k is positive, then it's a growth. If k is negative, then it's a decay, right? So let's go ahead and do number 15 here. Number 15. So you have 12 grams of radioactivity substance present initially, so that's initial 12 grams, and we only have 6 grams remaining. Okay, and then we don't know our k probably, which we don't, and then it's in 4 years, so we're trying to find our k, and then once we find our k, then we can write our equation. So this is finding half of the life, right? So again, isn't that just going to be ln of 1/2 over our years will give us our k? So we can go ahead and enter that in. So I type ln 0.5, close that parenthesis off, then go ahead and divide by 4, and we get approximately negative, right, because it's a half-life. So I should get negative because it's a decay. Let's do 3. Okay, that's our k. Now we can enter that in. Y equals our initial amount, which again is 12. And then e raised to our now our k, negative 0.01733 times our t. Now we can find out any year how much is left after any year, and they want to find out after 7 years, so then we can go ahead and enter this into our calculator as 7. So times that by 7. So remember, we can enter it just like this in our calculator, and we get 3.57 grams. So that's number 15. Number 17. Okay, so we're trying to figure out how long ago did the Egyptian die when he has carbon-14 1/3 of what is remaining. So that'd be 1/3 of our initial amount, right? And it's carbon-14. So really we can actually go ahead and enter in our K. We know what that is. We are given that as negative 0.001216, right? So we're going to get ln of 1/3. We're going to divide that by our K, which is negative 0.001216, and that's going to be our T in years. And so that is about 9,000